Okay, so thank you everyone for joining us today for this talk. Um, Today we'll be talking about brain and physiological data in computer science. My name is Horia Alexandru Mayor, and I'm one of the lecturers in the School of Computer Science at the University of Lincoln. Thanks once again for joining. As you can see, I've got a weird thing on my head, and this is one of the brain-computer interfaces or brain scanners that I'll be talking about today. And I hope I'll just inspire you a little bit and make you think a little bit what is the technology out there and what sort of things we can do with these portable sensors. So let's begin. There is a comment box, so please do put your comments in. Any questions you have, please feel free to type it in there. I've got it's right in front of me, and I'll be able to come back with a reply. So please do use that section, and let's begin. So before we move on, let's start with a question. I tend to use this example because it provides a really good understanding of the concepts that I will be talking about in this lecture. So all I want you to do is look at the next question and try to come up with an answer as soon as possible. As soon as possible. The triangle is to the right of the square. The square is to the right of the circle. What shape is in the middle? Quick comments, please. Anyone? So what shape is in the middle? Come on, we need a comment. Let's have a comment. Let's see if the comment box works. Okay, so is the square, yeah? So what if I showed you this? You know, what shape is in the middle? It's square again, yeah? Why? Which one of these was kind of easier? So which one demanded you more? Which one required more mental effort? Was it the first question or the second question? And probably you'll see that the first question was the more difficult one, right? So why am I showing this to you? The way in which we present information to people, it will impact how much effort it is required for them to produce an output or to respond to a question. The way in which we design a user interface or the way in which we design technology, it will impact the demands placed upon the people using this technology. So I hope I gave you kind of an idea about what we're talking about. If we design a more complex user interface, it will require more effort from the user. If we design a very similar user interface, but perhaps less complex, then we expect that people will cope better with that particular task. So what are the implications for design? When using a computer, people are already using a lot of resources. Therefore, if we were to design a computer program for them, then this should be taking as little mental effort as possible. You shouldn't think about the tools that you're using. The tools should allow you to do your work without taking much effort from you. For example, if you were to use let's say a search engine, Google, and if you were to use Microsoft Excel, these two have complete different requirements. So it's hard to compare between them, but definitely one of them will be harder to use. And we can change the user interface of Excel to try and make it friendlier for people who just start with it, for example. So what are the implications for design? We discussed that when using a computer, people are already using a lot of resources. When you are normally doing a task, you're using the computer as a tool, not the task itself, right? So the tool shouldn't take too much resources. So let's move on. Uh, More implications for design. How can we design a piece of technology that reduces the memory load, that doesn't require us to remember a lot of information or keep our mind busy with information, but supports us and presents useful information on screen for us? So it's about thinking all these implications for design from a very simple problem that we started with, isn't it? So don't make people remember the information, put it in front of them. Recognition over recall. So this is a heuristic that we have in computer science, which talks exactly about this. Do not rely on people to remember things. Put it in front of them if that information is important. Well, we all know that it is very difficult to start learning a new game, a new task, a new equipment, etc. However, if this is designed in a way that we've seen previous applications that have perhaps similar functions or have similar buttons, etc., then this will really support people. For example, all Apple phones will have a very similar icons. Will always have the actions are very similar in many applications, right? So there is some sort of standard or consistency there. Similarly, Windows will always have the cross on the right hand side of the top right corner, right? It'll never change, and this helps people remember how to close a screen. So very little problems that can make a big change in the user experience afterwards. So menu structures, the way we design components on screens. If we have technology out there that is already very much used by people, perhaps that's a good start point, right? To understand how their technology works and try and design something aligned or maintaining some sort of consistency. Make navigation clear and obvious. So this design principle, it's not new. The one I'm going to talk about, and it's back from 1991, and it is refers to computational offloading. What is this computational offloading? It sounds complex, but in fact it's not. It's thinking about how we can design a task that will make it cognitively easier to perform, right? So if we have to make a sat nav for a car and we're developing this, let's say we're working for TomTom, the question is, how can we design a TomTom application that will support users and will not generate a lot of mental processes? We need to think that the driver is already driving. He doesn't have a lot of resources to actually interact with this software. So the idea of computational offloading is finding the most suitable user interface or design that will best support the driver in this context, will generate less mental effort. And we'll talk a little bit about how we can measure this mental effort that I keep referring to. And we'll give you a couple of examples of studies where we investigated this concept of computational offloading, if you want. Okay, which brings us to our subject of the day, which is brain-computer interfaces and physiological data, and how we use this in computer science, and how it all started, and what a brain-computer interface is. So there is a definition of brain-computer interfaces from 30 years ago, which evolved to this one. The goal of brain-computer interfaces, or in general just brain scanners, is to give severely paralyzed people another way to communicate, one that does not depend on muscle control. And this definition talks specifically about a clinical population, patients who are suffering from a condition, people who perhaps are paralyzed, who cannot move, and for them, a brain-computer interface or a brain scanner like this is the only way they can communicate to the outside world. A fully paralyzed person can no longer speak. So how do you allow these people, these patients, communicate with the outside world? Can we use the power of thoughts to do this? So this is how the whole field of brain scanners, brain-computer interfaces started. About 30 years ago, once again, and it allowed patients to either communicate, to drive a wheelchair with their thoughts, to move artificial limbs just with the power of thinking. And I'll tell you a little bit about how this was done. And I hope you're going to enjoy this. So how does this BCI typically works? Well, usually using any sort of brain-computer interface technology involves a training phase where we teach an algorithm what things we want to train the algorithm for detecting, and the preparation stage. So in the image, you see a patient who's required to mentally visualize or imagine that he's closing both of his arms. The training stage would involve measuring the brain activity of the participant when doing this imagination stage. As you can see, he doesn't have a real arm. The left arm is missing. But he can still imagine that he would close both his arms. So imagination is not affected by not having an arm anymore. Yeah. So we can do this. And in the training phase, we would record 1,000 times a person trying to imagine closing both of the arms. Once the algorithm has been trained and we're done with this preparation stage, we fit an artificial limb to the patient's hand to replace his original arm, yeah, or affected arm. And what will happen? We will try and ask them to imagine they close their both hands, and when the signal is picked up by the brain scanner and the algorithm that we've trained, we can tell the arm to close, right? So this is how brain-computer interfaces work when it comes to direct input to an interface, like an arm, like moving the wheelchair, or actually thinking, how you feeling today, good or bad? And then if you think certain way, then the algorithm will pick up good. And then if you think another way, then the algorithm will pick up bad. So again, these things can be trained during the preparation stage. And we can use this to detect different things. So let's move on. A most recent definition, one thing I wanted to show is that I am not fully paralyzed, luckily, and I can still wear a brain scanner, right? So this is where the technology has moved. So most recent definition of BCI is a system that takes some biosignal, like brain data, measured from a person and predicts in real time or offline. So you either have a real-time classification of a particular state, or you analyze the data afterwards to learn about that person and what happened during that person while it was being scanned, in order to predict some abstract aspect of this person's cognitive state. And I hope this kind of made sense. How we use brain-computer interfaces today, once again, you can see that this person we have in front of us, he's not paralyzed either, or he's not got missing limbs. What he's doing there, he's controlling a game with his mind, right? So all this BCI research has shifted from clinical settings where we want to help fully paralyzed patients or patients that suffered a trauma and they are missing a perhaps limb, to the healthy population. So how can we use this technology to create meaningful interactions with technology, or to create, interfaces that are reactive to our state or our mind? So you can see that there's different applications from entertainment, medical, education, and of course, science. And we'll talk about some science examples at the end of this talk. There are different techniques out there to do scanning of different parts of your body. The top left one, the leftmost one called fMRI. I am not sure yet if any of you been in one, but this is a technology that is using huge magnets to scan someone's brain or body part. And as you can imagine, sitting in a tunnel for half an hour and just listening to boom, 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 it generates some real noises, um, can be quite immersive, but not in a positive way. It can be quite, um, it can quite affect you. You don't feel comfortable. You do not feel natural. So it wouldn't be right for us to put people in a tunnel and ask them to relax and watch a movie or ask them to play a game. That just doesn't work for computer science, right? Um, Therefore, we want to use more portable techniques, techniques that we can use perhaps to scan a player while playing a game, or techniques to scan an air traffic controller while being, performing tasks using a new interface. Or we want to compare the sat nav example. We've generated 3 different interfaces for a sat nav, or we've built 3 different sat navs themselves, and we want to see which one requires less computational work. Remember the computational offloading design concept. So we've got 2 examples here, something called EEG, that is, so this technology is using electrical activity and it measures your electrical charge released by your brain. And this is much more portable. You just have sensors on your head, electrodes basically. Some of these technologies involve some gel as well before you place them, and it can be a little bit ugly, but it's still way better than sitting in a tunnel for half an hour playing Mario, right? Okay, so the last technology that I'm going to talk about, FNERS, is also the one you see on my head, and this one we'll probably talk about it a little bit in more detail. So I'll get back to this actually. But what I wanted to show is that all it's using is some infrared light sensor. So this, compared to the other 2 technologies, all it's got is some infrared light sensor here and an infrared light receiver here. And I'm not sure if you've seen how your Fitbits or smartwatch or other wrist-worn bands work, but some of them have some sort of flickering light. Can any of you remember that? Did any of you see any of the Fitbits and the sensors, and how the Fitbit actually works? Is basically shining some infrared light to your skin here, but I'll explain this in a second. I've also got an interactive video to show you this, so probably it's better. Okay, let's go in a little bit more details with this technology I'm also wearing. Once again, this is using near infrared light to measure brain activity. Near infrared light is something that the sun generates. It's something that we can, just any kind of light in the right spectrum will do. So it's very non-invasive. So we are exposed to daily light every day, and nothing bad happened. So let's go a little bit more into details of how this works. As I told you, as you can see in this graph, there is something called an infrared light emitter, and you can see that right in the middle of this person's head or skull, and some detector. And the way it works, so once you shine light through your skull and tissue is transparent to light, and actually light goes right through it. And I've got, again, a video to show you and demonstrate this. But what happens actually, the light reaches your blood tissue and your brain tissue. And we've got a particular substance molecule in our blood called hemoglobin, which is the responsible oxygen carrier to the brain. So the way it works, when your brain or a region of your brain gets active, your neurons like to eat oxygen. When they ate all the oxygen, fresh oxygen needs to arrive in that area. That's the neuron's food. So the way this works, in our blood, we've got this responsible molecule called hemoglobin, and this molecule will bring fresh oxygenated blood in the area that requires more. Yeah. So hopefully this made sense. I've got, in the next slide, I've got a nice video for you. But yeah, I didn't finish, sorry, with this slide. Once the light reaches this area, hemoglobin is got a property that absorbs light. So you've got more hemoglobin, more light will be eaten by it, and less light will be refracted back on the light detector. So we can see very easily using this brain scanner when I've got more or less fresh oxygen in my left part of the brain, in my right part of the brain, or in any of these different channel locations I've got on my forehead. And this is heavily indicative of brain activity. Once again, your neurons need oxygen to function. When an area gets active, more oxygen is required in that area. Therefore, more hemoglobin will bring fresh oxygen. Therefore, less light is gonna be, more light is gonna be absorbed by hemoglobin, and less light is gonna be refracted back. Okay, so let's move on. I've got a little video for you. I'm not sure how much time we've got to watch this, but let's start watching it, and then we'll stop if we need to. So I think that would be enough. I've got so if you actually Google how we can use light to see deep inside our bodies and brains, you'll find the full TED Talk, and I really recommend you watch this if you're interested. They also have a jar full of blood, and actually they put some light through it, and you can actually see how the whole light is being absorbed by the blood. So they kind of show you and prove you these concepts. But hopefully you saw that using simple infrared light, we can spot tumors. We can detect, differences in different brain regions. And this is exactly how your Fitbits work as well. They shine some light to your wrist. Sorry, okay. And when your pulse goes through, there is a higher debit of blood. All right? Boom, boom, boom. Therefore, more light is being absorbed and less light is being refracted back. And that's how they can measure your pulse. Using simple light, just the light, we can measure pulse, which is pretty fascinating, I think. Okay, so hopefully now you've got an idea about how this technology works. We shine light to my brain, and then if more light is being absorbed here, then less light is going to be sensed by the sensor. And of course, we've got different locational channels here, and we can get an idea of what happened in my frontal part of the brain. There are sensors that cover the whole head, and this will depend on what area of the brain you're targeting. But as you can see, this headband is being designed for the front part of the head. So how can this be useful for computer science and human-computer interaction? There's three types of BCI. There's something called active BCI, and is the one where a person would voluntarily control something with their thoughts. And I'm not sure if you've seen this, but there's many videos out there with people flying a drone with their minds. And this is a best example of an active BCI. You purposely control with your thoughts a drone. The way they do it is very similar to the way I explained it to you earlier. They actually use imagine to close both hands, imagine to close only one, imagine to move your right foot. And using these imagination actions, you can actually turn left. So if you imagine that you close both of your arms, you set that to take a left turn for the draw. So this is exactly how these systems work. We've got something called reactive BCI, and this is still focused on control, but a little bit different. So when something happens outside, then some sort of indirect. How should I best explain this? So the purpose is still controlling an application, but this is done indirectly of the user. So the user wouldn't actively think in order to be able to perform a change, but a change happens at certain points when let's say the user reaches certain thresholds. And the last one is the passive BCI, and this one has got a little bit of a different purpose. This passive BCI, so let me just give you an example of reactive and passive so we can distinguish between the two. So imagine you're an air traffic controller working and managing airplanes, and you've got about 30 airplanes to manage, and you're getting pretty stressed out. And because you're wearing a brain scanner, we can measure that. We can realize when you're really thinking very, very, very hard, and when you no longer have resources to cope with what you need to think. Well, in that case, maybe the system will automatically take 10 airplanes from your screen and move it to another operator. Therefore, the task you're doing reacted to your state. Yeah? So you can see that you no longer actively imagining to close hands in order to take a left, but the system adapts based on your state. And the last one is a passive BCI, and this typically involves scanning a person in different states. For example, when they sleep, when they perform a very difficult task, when they perform a very easy task, and then trying to understand what happened in their brain in these different states. Yeah. Okay, I can see it's half past, so we don't have, I think we've got about 10, 15 minutes at most left. Okay, so computational offloading again. We came back to this because now we know a little bit more about the technology, and we know a little bit about what we can study using this technology. So if you think again about performing a simple task, let's call it a search task, and I'm going to ask you to find the last University of Lincoln term times. So if I'm going to ask you this, which tool would you use and why? And which one do you think will support better the user during this task and why? And I mean, the opinion may be split here because, yeah, it might depend on what people are already using or used to. But maybe there will be a preference, and we can use a brain scanner to study this, to study how stressed people are when performing this task using one interface against the other. And this was just an example for you to understand how we can study the impact of different software or technologies on people and how we can choose which one is better. And this brings us to a term called mental workload. And mental workload, maybe you've heard about this, refers to the amount of effort expended, perceived, so how people feel about what they are doing, and experienced by an operator whilst completing a task within a limited time period. And this is important. As human beings, we have limited capacity. That means we can perform a limited set of tasks at any given time. And this is exactly how this model is called. It's called limited resources model. And this basically says that, we've got a limit, and basically that's when we reach our maximum available resources, Once we run out of available resources, we can no longer cope with the task. Therefore, if you see a dotted line in this graph, when the allocated resources reach a point very close to the maximum resources, our performance, the dotted line drops. And for design, it will be key to understand how much resources Bing requires for the task and how much resources Google requires for the task, and then compare between these two and see which one supports the operators best, or the users best. And you can also see on this graph the concept of spare capacity. So if we're doing a task that doesn't take up too much resources, then we've got a larger spare capacity. If we are doing some very difficult mathematical problems, then we probably have little spare capacity left. And if somebody asks you to do a secondary task, like asking you what the time is, your performance with the mathematical task will be affected. And that is exactly because you reach your maximum resources and you're in your head, just leave me alone, I want to solve this math problem, you're interrupting me. Yeah. And that is exactly because we run out of resources. So in the next few slides, I'm going to show you some study examples, some more interesting, some you might find less interesting. Just take whatever you feel that helped you or inspired you from this. In this study, we basically, I'll play this video because it's a nice abstract.
There are many aspects of usability, but one concern for user interfaces is to reduce mental workload and error rates. We examined the use of functional near-infrared spectroscopy as a tool for measuring mental workload during usability testing. We used this technology to evaluate the design of 3 different form-filling layouts for a car insurance claim process. While no differences were found in emotional or performance measures, using FNIRS, we showed that dividing the forms into separate pages significantly increased workload.
Okay, so this study was about something we do every day, filling forms. And filling forms is not fun, and some forms are easier to fill than others. I know it's a little bit of a strange task, but this was the task that we wanted to use, and we wanted to find out more about how to design really good forms. In this study, we used a very, very, very strange task. Participants had to watch a car accident, a video of a car accident from the driver's perspective. So we had some dash cam videos. I think it was selected from YouTube. And after the crash, participants had to use 3 variations of a form, or they had to fill one of these 3 forms with all the events that happened, almost as if they were filling in an insurance form. So we created an insurance website where you'd report what happened during an incident using different style of forms. So this was just to give you a little bit more context, but what we found was
there are many aspects of...
Okay, so this was it. But what we found was that there's different ways in which you can support the operator, and if the form has a particular design, it will impact participants' performance. In particular, we found that if we divided the forms into multiple pages, people found it more difficult to complete this task, and this was again related to perhaps the information that you no longer see. So once you submit the first part of the form, you no longer see that part in the last condition, in the index 3. So perhaps that information was important, and this is why it generated more mental workload and more brain activity. Yeah. Another example of a study looked at measuring a person's brain activity while performing a task and providing them with some feedback. And what we did, we hooked them to a brain scanner. We did the preparation stage or the training stage, in which we detected when they are getting bored or when they are getting overstressed. Yeah, so if you remember that limited resources graph, we had one condition when they were very, very less demanded or little demanded, and one condition when they were very highly demanded. And based on this, we classified their brain activity in real time. And then if we detected that it was a high workload state, we turned all the office lights to red in real time. And if they were sensed to be on a low workload, then the whole light in an office space will go to blue. And this was just to give an idea to the user about where they are on that graph. I'll show you a little bit of a video again. Basically, they had to perform an air traffic controller task. Well, simulator game. You can actually play this online. It's called Airport Madness 4. And you can see the participant, he's hooked to the brain scanner. There's different actions you need to do in order to fly these planes and manage the planes. The idea is do not crash any of them, right? Oh, and you can see that the lights just turned red, and the participant was also, yeah, somehow perceived that and laughed. But this is a real-time system that is using, it's a reactive BCI. The example that we talked about, when we're getting to a very stressed scenario, perhaps some of the work can be redistributed to some other operators. Especially in critical systems, we do not want people to fail. There isn't a fail when it comes to air traffic control. People cannot make mistakes. So how do you ensure that they are on the right workload level? And this is why these technologies are so important for this field of research. Okay, so this is some more details about the study. I'm not going to go through this. But as you can see, this graph is interesting because you can see here, yeah, you should look at the right-hand side graph. So in the right-hand side graph, you can see demand, and oxy stands for oxygen in the brain. So it's actually the brain activity. And the demand is the left side scale here, and is the number of airplanes they were controlling at any one point. So you can see that as the number of airplanes on their screen increased, and they had to manage more and more aircraft, and you see they have more than 10 in their visual space, the workload increases, and it's got a very, very, very close match with this. So when the demand decreased, the brain activity decreased as well. So it was quite reactive. Let's take another example from another participant. Once again, let's look at the right-hand side graph, because that has got the brain activity versus demand again. So once again, the demand is the number of airplanes they have on the screen. And as this increases, the brain activity very, very closely follows this pattern. Yeah. And this was one particular area of their brain. Let me just take this off. Non-invasive, but you know, it's a band that presses your forehead, so maybe it's better this way. Okay, so we've got 5 minutes left. How do I get my mouse on the other screen? Okay, I'm gonna jump over these findings because I didn't talk too much about it, but let's move to the next study. This is maybe more interactive and interesting for you. So this study looked at facial thermography. So we take a break from the brain activity data. This was a study conducted by Adrian Marinescu, and he went to Airbus, and we worked with them in order to estimate the mental workload of pilots, of helicopter pilots during different scenarios. And this is an Airbus pilot in a high fidelity simulator. So he's not in a real helicopter, he's in a very, very high fidelity simulator of a helicopter that actually moves and provides all the interfaces that a normal helicopter will have. And we've selected a difficult scenario for this. In the next 30-second video, you'll see the operator, and you've got the facial thermography. So this is using infrared cameras to scan people's face temperature or skin temperature. And what I want you to look at, I want you to look at the nose tip of this operator. The scenario he's going through, his airplane first engine just failed. and then he's trying to get that back, and then the second engine hits and fails, and then the whole scenario ends up with a crash. But what I want you to have a look is the face temperature, and also the nose temperature, and then we'll talk about it afterwards. Yeah. Okay, so you can see the different points we track on his face, and you can see his face goes reddish. And look at the nose, right? So first engine failure happens now. He's getting stressed. Second engine failure happens now. He's, his head is like a bulb. And look at the nose. Okay, and we're gonna end up with a crash. You're gonna see him move heavily, and he's laughing. So luckily, this was a high fidelity simulator and not a real airplane. But using this high fidelity simulator and physiological data, we can learn how people cope under stress, how their physiological data changes under stress, and therefore we can detect it later on in case we want to. Yeah. So we did a follow-up study to investigate this in more detail. This is my face when I used to have some more hair. You can see it's gone. But that's my facial thermography scan. And we did another study looking at how this facial thermography changes with your brain activity, task performance, and subjective data. So what I'm going to show you is an experiment here that used different physiological data, performance metrics were recorded, and subjective data. And you can see the setup. They had to shoot balloons. So this wasn't very much like flying helicopters, but we picked this task because we controlled the number of balloons they had to shoot. We increased the number from 1 to a very high number, so we can play with how much work they have to do. And using a joystick, it was quite difficult to perform the task, so that added more complexity. So you see, in a lab setting, you can use any simplistic tasks that you can model, because you can model them better in order to understand what happens in the people's brains. So we tracked different points on the face again, and as you can see on the top image here, you can see how demand increases. So the number of targets they had to shoot on the screen ranged from 3 to 17, and then decreased again. Increased, decreased, increased, decreased. And what did we find? This is the task. They had to shoot balloons. They had some performance metrics as well. But what did we find? We found out a very, very, very close relationship with physiological data, performance data, and demand. So you can see those 3 peaks happening here again. The red line here is the nose temperature. So you can see that the nose temperature of people went down as they had to work harder. So as we have higher mental workload, our nose tip gets colder. And similarly, you can see the brain activity is the blue line on this graph. You can see the blue line here, and then we had how they reported they felt. So that follows a very, very close pattern. So these all data points were very highly correlating. So you can see how we can use this in order to study people better. And the last example I have today is a bit scary, I think. Measuring mental workload variations in office work tasks using a brain scanner. So there's been some media articles. I think last year they started with different companies in different countries scanning people at work, which is very sensitive topic to talk about. But this paper didn't have at all this intention. It was mostly looking at how when we read things that are easy, medium, and hard, and how when we write things that are easy, medium, and hard, how our brain activity changes, and how and if we can use brain activity data to detect this. People had to fill in some questionnaires after each condition. So that's what the bottom graph is. So you can see reading easy, reading medium, and reading hard generated different levels of difficulty felt by participants. And on the top image, we see here. Oh, let me see if there's any questions. Oh, thanks, Ben. Ben had just a comment, not a question, that this is interesting. Yeah, we'll talk about this, Ben, how we can do a study together as well to study drivers with this. And I think we should do that for sure. But basically, let's go back to this study. So you have the brain activity data on the right-hand side. And there's two types of measurements, but the brain activity is the space between this line and this line. So you can see that, especially from reading medium to reading hard, people brain activity expanded. So once again, the brain activity is the space between the blue line and the black line. I know I kind of rushed through these last slides, but what I'm going to do is, if people want a copy of these slides, please do email me at the end of this talk. I hope I have my email address on the last slide, so please do send me an email, and I'll be very happily share this set of slides with you. Yeah, and for the writing task, the brain activity didn't pick up any differences, but you can see that there was also these weren't that clear in the subjective data as well, and we blamed this reason for it. Some of the projects that are happening now at the University of Lincoln, I'm working with some students on some really cool projects. One of them is using brain and heart rate data for a game, and it's this idea that when we play, when you're perhaps performing a task, I think we looked at shooter games, right? But the idea is, if you're very, very stressed in real life and you're a sniper person, I'm not sure how this works, but I imagine that if you have a very high heart rate, it's going to be very difficult to hold your to actually have a really good performance. So we're trying to simulate that. If a player is is immersed in a game in virtual reality, a shooter game, and his heart rate pumps up, then perhaps his ability to perform a shooting action should be influenced, and it should be harder for him or her to actually perform a shooting action, right? Just to simulate how this will work in reality. If you're very much stressed, if you have a high heart rate and you're being stressed, then your abilities reduce. So we're trying to simulate that in a virtual reality game. Another study, we're looking at how we get distracted by different tasks. So if you're already working on something, writing something, and then you get the text notification, when are you likely to react? What sort of brain activity triggers will we be able to sense, etc. And lastly, studying the human-robot interaction using brain and physiological data. So interacting with a robot will be more complex perhaps than interacting with a normal computer. Therefore, these and especially robots that perform critical jobs like nuclear waste and teleoperation in a medical field, these interfaces need to be very, very well studied, because we do not afford a nuclear waste error that can cause a lot of harm. And this is why it's so important to study these the best we can. Well, finally, I want to say thank you so much for taking part in this talk. Please, if you have any questions, I am monitoring your comments box, so please put them now. I just saw that there isn't my email address on the last slide, so what I'm going to do, is it on the first slide? No, it's not. So let me just write it down now. If you bear with me 1 second, I'll do that now. And we're going to the last one, and we just want to add, okay, we'll just add it here, and it's Okay, so if you can email me, just say you want a copy of the slide. I'll very happily share that with you. All right, so any questions? Anything? If there are no questions, okay, I'll give you 20 seconds. Questions? No questions. Okay. Well, once again, I would like to thank everyone for joining the session today. Thank you for your patience and thank you for listening. It's been a pleasure to do this lecture, and I hope I inspired you a little bit. Thank you once again, everyone, and have a great day.